cyber weapon from 2005 just rewrote history. It wasn't loud. It didn't blow up systems. It changed math, and no one noticed. This is the story of FAST16, the first known tool built to corrupt high-precision software at scale, years before Stuxnet ever hit Natanz. In 2005, a piece of malware named SVCM-GMT-exe was compiled, disguised as a standard Windows service. It carried an embedded Lua 5.0 virtual machine, encrypted payloads, and a PDB path pointing to a kernel driver. FAST16. SIT. That driver wasn't just another rootkit. It sat deep in the storage stack, intercepting executable files as they loaded and patching code in memory. Its mission: to subtly alter the output of high-precision calculations. By 2017, the name FAST16 reappeared inside the Shadow Broker's leak of NSA tools, listed as a deconfliction signature. That meant it was so sensitive, US operators were told, "Nothing to see here, carry on." This was random malware. It was a state-level sabotage framework, built to infect entire facilities and produce silently wrong results in critical workloads: physics simulations, nuclear modeling, cryptography. FAST16 wasn't designed to crash systems. It was designed to make them lie. That's a fundamental shift in cyber warfare. Most attacks want attention. Ransomware locks screens. Destructive malware wipes disks. Stuxnet blew up centrifuges. But FAST16, it wanted to stay hidden while corrupting the very foundation of trust: computation. Imagine a nuclear lab running simulations. The numbers come back consistent. The graphs look right. But every result is off by 0.3%. Not enough to raise alarms. Just enough to derail years of research. That's the nightmare FAST16 enables. The technical architecture proves this was no script kiddie project. SVCM-GMT-exe used Lua, a scripting language that allows dynamic code updates without recompiling. That's advanced for 2005. Flame, often credited as the first Lua-powered malware, didn't appear until 2008. FAST16 predates it by 3 years. The developers extended Lua with native Windows API access, Unicode support, and encryption, all packed into a modular, reusable framework. This was a one-off hack. It was a platform. And then there's FAST16, sys, the kernel driver. It sits between the disk and memory, patching executables on the fly. No file on disk is altered. No antivirus alert. The binary runs with corrupted code, produces bad math, and shuts down, leaving almost no trace. Combine that with self-propagation via weak network shares, and you have a worm that spreads silently through research facilities, ensuring every machine produces the same incorrect results. Why does this matter now? Because we're entering an era where AI models are trained on petabytes of high-precision data. One corrupted simulation in a climate model, one tampered number in a drug discovery pipeline, and the downstream AI learns the wrong physics. FAST16 was just a tool for the 2000s. It's a blueprint for sabotaging AI at the data level. The real threat isn't data breaches or downtime. It's the silent poisoning of computational truth in systems we trust to be objective. As AI relies more on high-precision computation, the attack surface shifts from stealing data to distorting it. FAST16 proves that capability existed nearly 2 decades ago. The question isn't whether it's being used today, it's where. Watch for anomalies in scientific results, unexpected model drift, or unexplained inconsistencies in replicated studies. The next cyber war may not crash servers. It may just make everyone believe a lie.